and welcome to Chapter 12. In Chapter 12, we're going to discuss distributed database systems. So in Chapter 11 and 10, we talked a little bit about a distributed system simply being that it was something that was split and you did it with large data sets, but we didn't really get into what is it. So for this chapter, we're going to talk about how to build a distributed data system, what it is, how to build it, and the benefits that come with it. Let's get started. The first part of this chapter will discuss the evolution of a distributed database. Why did we start doing it? What was it that was important about our database systems that we had to expand upon them and build a distributed database? In this slide, we start with the things that occurred, what we did about it, and then the solutions therein. So essentially how things changed over time. First off, operations in the country and in the world became global. Everything meant that you didn't have to be next to your customers anymore to be able to serve them and to provide them information. You didn't have to be next to your office anymore. Everything was global. The thing about being global is that it has to go across the internet to get to anything. And being far away from things no longer became a limiting factor or requirement of your company. Everything could now be remote, or it could be from multiple locations. So we had to take into account you might have some employees that are from New York and some that are from California and some that are from Montana. And how do you make them all work together? There was a huge increase in on-demand or web-based applications. People want to do their jobs. They want to be able to buy things from all hours of the day. They don't want to follow that 8 to 5 concept of, it's now 5:02. I can't go buy the new thing I want to buy because it's after hours. We don't do that anymore. Everything is now web-based. It's all on demand. The increase of mobile applications. So back in the early 2000s when we had BlackBerry and that was this new concept and we started being able to text, and then suddenly we were able to add new things to that. Only in the last 10-15 years have we actually had the ability to have applications or apps on your phone that were able to do things that were significant, more than just making phone calls or being a calculator. Now you can have a full-blown app on your phone that does everything. So we needed to be able to take that into account. Obviously now, with cell phones, mobile devices, it used to just be that it was data. It was pieces of information, but now it's images and music and videos and things like that that have to be transferred as well. And that means, again, that distance that comes with being a global society means that we need to take that into account when we're making our database. We need to know where the data is going to be, where it's going to be stored, and how it's going to be accessed. And then, of course, with social media and big data, there's such a huge amount of information out there, and how can you as an employer, as a company, tap into that piece of information to be able to get more customers, or to be able to help your employees better, or help your vendors. So these were all issues that people were running into, and we have solved a little bit of it by building distributed database systems. Two things that were really important that we found out of these 5 things that were going on in the world is we needed to have rapid ad hoc data access. Now the ad hoc, if you haven't ever heard it before, simply means they don't know ahead of time what data we're going to need. We don't know ahead of time. We want to be able to do things on the fly. We want to just ad hoc things as we go along. So we wanted to be able to get data access without it being like scheduled. We wanted to do it on our own time. We also wanted to be able to have that data access be distributed amongst multiple locations. If I have clients that are in New York, do I want to have some of my database servers closer to them so that they can access that data faster and easier because of that distance issue? So we looked at that and we said, okay, these are some things that we need to take into account. First off, your willingness of your company to accept the internet as it exists. There's a lot of people that are kind of stuck in their Luddites of, we don't want to move on with databases, we don't want to move on with the cloud computing, we don't want to move on with the internet. But a large percentage of people have started to accept it. Cloud computing exists. It isn't a bad, terrifying thing. Microsoft's going to come take over the world. Cloud computing became really useful. So there's acceptance that people have had for using the internet and having their data available on the internet. I've met people who do not want to use QuickBooks online because they're afraid QuickBooks or Intuit is going to take their data. That feeling is going away. People are getting more and more comfortable with the internet existing and being able to have their data there. The mobile wireless revolution, the simple fact that mobile wireless is now able to do 5G in some locations, it's able to have all these huge apps that are on your phone, that your phone is so powerful. You know, if we had to go off the requirements of our phone, even from 5 years ago, we wouldn't be able to run half the apps that we do today. So the advancement of wireless technology on your mobile phones to be able to have that app right at your fingertips. The application as a service, or software as a service, SaaS, became a new concept of, instead of having the application be something you installed on your local machine, you ran it off your local machine, now we go to a website and we run it from there. A lot of company software used to be a piece of software that you would install on your local machine. We don't do that a lot. Now we do a lot of web-based things, specifically because of this mobile technology. The idea that if you installed it on this machine and a new customer came in, or a new employee came in, we need to install it on their machine, and it kind of became a pain. But having everything as a service, being able to do this idea of everything's being web-based, helps a lot in that situation. A lot of business owners want their information, and they want it literally the moment they ask for it. They don't want to wait. It used to be, I would go, you know, you could go and ask somebody, hey, can you get me this information? Yeah, I'll get it by the end of the day. I'll get it by, you know, 2 or 3 days from now. That isn't acceptable anymore. Everything needs to be instant. It needs to be instantaneous. I need the information right now without question, and you have to be able to get it. So that on-demand concept of business intelligence, I can't make a decision until I have the information, comes into distributed databases. And then last, the big data, which goes back to social media. How do you take into account that this person just searched for dog food to be able to turn that into something you can use for your advertising, that you can use to draw business to you? How can you use the information in big data to be able to get more customers, make more money? Because it all comes down to profits. Okay, so this is where the evolution of distributed databases. We realized things were moving along and we couldn't keep up with it by having our database server sitting in the back room anymore, because that just wasn't going to cut it. We had remote employees, like what's going on right now, or we had employees in different locations. And how did you handle that if everything was on a server that's locked down? We had great physical security, but nobody could access it unless they were in the building. So that kind of thing runs into this distributed databases. If we're not going to have it in the building anyway, what can we do to make it the most efficient so it's the shortest time to get from the database to you, and to help your customers and your employees work better? When you have a centralized database, so you have a database that's sitting in a server in the back room, there are some issues that are going to come in. First off, you're going to have a little bit of performance degradation, meaning that if you have more different remote locations, you're going to have more distance between your data and the locations. That increase in distance is going to cause your performance to go down a little bit, just because it takes a little bit longer to get the data from point A to point B. Now, our internet is really smoking fast and we're doing great, but the more data you're sending, if I'm sending huge video files, sometimes it takes some time to get there, and the closer the video files are to you, the shorter the time is. So simple performance degradation from simply being at multiple locations. Your costs, the costs of maintaining and growing a large mainframe and the infrastructure therein. This is where cloud computing has really come in, because you can tailor your server on the fly, and you can say, okay, right now I want this size server. Oh wait, now I need more power, I need more RAM, I need more. Let's just upgrade it. And I don't have to go down to a store, I don't have to buy anything, I don't have to wait for it to show up, and I definitely don't have to install it on my machine. I just push a button and it upgrades it automatically for me. So the cost of maintaining the large mainframes is starting to get to be cost prohibitive for a lot of people. It's just not worth it for them anymore to have a network guy who works at the office making sure that the temperature stays right and everything's taken care of. If we need to upgrade RAM, if we need to update disk space, those kind of costs really start to come in. Of course, there's a reliability issue. It's the all eggs in one basket concept. If I have one server sitting in 123 Main Street and 123 Main Street loses power, I lost my server. It's gone. Or at least it's down and unavailable until I get power back up. If I have a fire and it burns up my server, it's gone. If I have my backups all in the same location, again, it's a reliability issue. By having everything in one location, you run into risks. Our scalability goes back to that concept of the physical limitations. If you can't buy another server, but you could do it on the cloud. You could do it in a different location, but you literally don't have the room in your server room to add another server. If you have been in the server room over in Great Falls, you know it's kind of packed. If we wanted to add 10 more servers onto there, it'd be a little more packed. There's always physical limitations of where things are going to go, whereas being able to centralize or being able to distribute them will allow us to have servers in multiple locations wherever we have the space. And then, of course, there's that rigidity that comes with an organization of this is what we're doing. How hard is it to change? We don't like change. If you want to upgrade your server, if you want to get the newer version, how many people are still working on SQL Server 2008 because they're terrified of upgrading to 2014, more or less 2018? How many people are still stuck on Windows XP? Same concept. There's that rigidity that comes with it all works right now, let's just stick with it. Yeah, but it's old and it's antiquated and you don't have all the best little benefits that come with the new or upgraded version. Well, yeah, but it works now and I'm terrified of changing. So you're going to run into that concept of you're not going to be able to upgrade as easily if you have a centralized database because you're going to get stuck in it and you're terrified to change it. So these are just a couple of issues that you run into simply with the management of a centralized database. That doesn't mean a centralized database is bad. And in a lot of cases, it's perfect for whatever you need it to do, as long as you recognize where the fallbacks are, where the problems are that come with a centralized database. Let's move on. With a distributed database, there are pros and cons, and it's important for you to recognize the cons just as much as the pros. So the pros, obviously distance. If the data is closer to you, it's faster to get data access. So that's generally a pretty big pro. There's a concept called parallelism, which is the idea that multiple workstations can do different processes at the same time. Makes things go faster. If we had to do them in serial, if we had to do one after the other, it would take, I don't know, 5 minutes, whereas if you could do them all at the same time, it might only take 3. So being able to run multiple items through your database at the same time, through different versions of your database, will allow parallelism to allow you to spread it across multiple sites. Obviously, growth becomes a big issue because if you're already distributed, adding one more server isn't as much of a big deal. You can say, hey, we just opened a new store in Raleigh, so let's go do a new server there. And it's not as hard to do if you already have 5 other servers around the country. So growth becomes kind of more of an easier idea. Your operating costs are smaller. That doesn't mean all of your costs are smaller, but the operating costs are smaller, which means if you have a database and you're being charged by the gigabyte, by the transmission load, because each database is technically smaller because you can fragment it, it can decrease your operating costs. That doesn't mean all of your costs change, but that can reduce your costs there. Because your server, your database server is close to your customers, is close to your clients, is close to your employees, you can have some better interactions, better communication. You can have processor independence so that your processors can access data from any location, but you don't care, you don't notice. So if your location is overloaded, it can say, you know what, I'm going to go over to that other one that's in the middle of nowhere that no one's touching, and I'm going to go access it from that data, and it's all good. It does it automatically, and your server has that accessibility open of using all the different sites all at the same time, depending on workload. So your interactions with your users is easier because they have access to that data quickly. And then, of course, that reliability, the eggs in a basket concept. If one of the servers goes down, do you really even notice? Because if the other servers pick up the slack, you should be okay. So being able to distribute it and have it all set up that way makes things really safe as far as reliability. There's no single point of failure. Now, if they all go down at the same time, that's a completely different story, but the odds of that, especially if they're in remote locations, is pretty slim. So those are the pros. Those are all the good things. Let's look at the bad things. Big one with the cons is complexity. You have to have a DBA who understands distributed data systems because you have to coordinate the activities. You have to understand the difference and being able to change the way your queries are based on how the distribution is created. And we're going to talk about that in a second. Different types of distribution require different things from the query. I might have to say, hey, I have to know the location of the server I'm going to. So I may specify that in a query. My applications may need to know that. And some data may be built from different locations, which means access time might be delayed because I'm waiting for information from a different location. If I put all of my customer information in one location and all of my employee information in another location, and I have to get data from both, my time might actually be slower in that case because it does have to get data from multiple locations. There's always the fun technical difficulties. If you have to make modifications to handle the parallel workloads or optimization of your queries based on the technical aspects and where they're located, might just cause a little bit of annoyance. It's kind of like, I'm not quite sure what I'm doing here. Needs a little bit more skill. So that's kind of one of the problems that come with doing a distributed database. If you have a DBA who isn't comfortable with a distributed database, it makes things a little bit harder. The security issue actually becomes a negative because data management isn't just one person, and it's not just one room anymore. Physical security in a server room used to be one of these things where one guy had the key, no one else could physically get in, and there were things that guy could handle as far as making sure nobody else was able to access the data. If I have 10 different servers all over the country, I don't have one guy with a key anymore. So there's a security option of distributed databases that kind of gets lost. You don't get as much security issues. And then, of course, the increased cost. So we said there was a little bit of decreased cost with your operating costs, but there is an increased cost, which is obviously you need to have a place to store the new server unless it's on the cloud. The additional training costs, again, you need a more advanced skill set to be able to work with the distributed databases and make sure you understand them. So it's not just your regular DBA. You need somebody who has experience with distributed databases. And then, of course, duplication of infrastructure. So if I have 2 servers, I need to pay for the rent in both locations. I need to pay for the lights and the power. All of those type of things get duplicated. So those also increase your costs. Generally, when you make the decision to switch from a centralized database to a distributed database, you very rarely start there. Most companies don't start with, 100,000 people. But when you build a distributed database system and you transition over, you're usually in a situation where you're going, the time and the response is so slow that I need to make something different. And I know it's going to cost me more, and that's okay, because the most important thing of my database is getting the information to my user, and that's starting to be a problem. So this is where we kind of go over the pros and cons of distributed databases. So with a distributed database, we have 2 different things that we need to keep track of. The first is the distributed processing, and the second is the distributed database, and we can do both. So distributed processing generally refers to a singular database in a singular location that allows multiple workstations to access it. So if I have one server sitting over at the school and I have workstations in Helena and Billings and Missoula, and each of those can access the one out of the school and use that database. That would be distributed processing, in that the processor for each of the 3 different computers at the different workstations is able to do the processing, but the database holds the data. So we have to go get the data from the database, bring it back, and then process it. So we have our processing. Logical processing is simply shared among 2 or more physically independent sites. They're in 2 different locations. The database still can reside in a single location, but the processing is distributed. The other is what we call a distributed database. Distributed database actually takes the database and splits it into fragments. Those fragments can be stored in multiple locations. And those are stored in independent sites as well. So again, we would have a fragment of a database in Helena and a fragment of a database in Missoula. They can be either replicated in multiple locations or fragmented. So we'll get into a second about the difference between the 2. But the idea being there's data that is stored locally at the site of each of your workstations. So if I have a workstation in one location, it has a copy of the database in that same location, which causes my speed to be much faster. So we've distributed the database and we put it in 3 different locations. When we split it into what's called fragments, and we're going to discuss the difference between splitting it or replicating the database. Okay, so these are the differences. You can do distributed processing with a singular database. So that's fine. You can just have the processing be done. This is what usually happens if you have a lot of client-side scripting that is being done on the client rather than being done on the server. That's a type of distributed processing. The processing is being done locally and the database is stored elsewhere. So when we have a DDBMS, or a distributed database management system, it holds all of these different characteristics. And I do want to go through them and just kind of give a one or two word example of what each of them are. So starting at the top, we have our application interface, which is simply the way that we interact. This is usually a website or some semblance of an application. You can do a Windows app for this, but a lot of times it's a database, or it's usually a website so that you can interact with your database. When we log into SQL Management Studio, that's an application interface. We're interacting with our database. Validation is simply the concept of being able to validate our data, making sure that the right people get the right data, that we have our syntax correct, so forth. Transformation is where we take the queries or the requests and we break them down into what we call atomic requests or simple requests. So if I had 3 subqueries, 2 where clauses, and a having and a group by, I need to break that down. So which am I going to do first? Well, I'll probably do one of the subqueries first, and then probably a second one, and then depending on how they're connected, I might do a join at that point, or however. But breaking that down into its individual atomic requests so it can get the data. An atomic request generally is select something from table, period. Usually maybe with a where clause, with some sort of a restriction on it. But it's going to be select something from a table is a single atomic request, as opposed to aggregating or joining or things like that. Query optimization we've talked about, but that's simply finding the best fragment when we do query optimization with a distributed system. So if I have multiple fragments, which fragment should I be looking at? It also begs the question of should the data be synchronized? And we'll talk about synchronization in a couple of slides, how the data gets synchronized to make sure everybody gets the right data at the right time. Obviously, we're going to do some mapping where we're going to say that this location holds this data, this location holds this other data, and we're going to have a map between all of our data types and all of our locations so that we know where what data exists so we can access it. Obviously, there's the I/O interface, which is how do you interact between the server and your cache. Remember, you might have a local cache as well, but this is the server's cache. This is the RAM on the server. Versus how are you going to interact with your client. So you're just simply your interface between your input and output from the disk drive into your RAM or your cache. Obviously, formatting is going to prepare all the data for the user. That's being able to take your query and be able to turn it into something that is a record set for your user. So we're going to format it and make it pretty. Security, obviously data privacy. We need to make sure that the locations are secure and that there is privacy so that things do not get lost in between time, especially if they're being transmitted over the internet. If that internet is open, if you're going through servers that are more risky, be careful about those. So data privacy is always an issue with your distributed to make sure that the data in between 2 locations is not available to be hacked. Backup and recovery, make sure that your database can be backed up. Same way you would with a centralized database. This is just making sure you can recover your data. If you have it in multiple locations, how do you recover half of the data? How do you respond to just little breaches or little backups that you need to do between multiple locations, and how is that handled? Your DBA, just your interface for being able to get into your database from a DBA. Again, this is back to a studio so that you can interface with your database without being in the same room. Concurrency, remember keeping your data current. How do you manage data consistency across multiple fragments, which becomes a problem? And then of course transaction management, where you want to know, how do I keep my transactions to make sure that I have consistency? How do I handle a transaction that's going to go from one fragment to the other and combine them together? Okay, these are all different things that we're going to kind of touch on in a couple of slides as we kind of go through this, but these are things you want to keep in mind when we're thinking about a distributed database system as opposed to just a simple DBMS in one location. This would be in multiple locations. All right. When we have our DBMS, we need to actually build it. So there are different components of a DBMS. First is what we call our transaction processor, our TP. Our transaction processor is the piece of software that sits on the client's machine or on the workstation. And it's the thing that knows how to get its data. So it knows how to get data from the database wherever it may be. So this can be an individual application. This can be a website, usually written in like a client-side scripting language like JavaScript, that allows the website to go get the data from the database. So this is the transaction one. He's processing the transactions, but he's sending that over to the database to pull the data. So he's just dealing with transactions at this point. He is sometimes known as the application processor or the transaction manager. I generally will refer to him as TP or transaction processor through this, but some people will refer to him differently. Application processor, he handles the application. Transaction manager, he manages the transactions, but they're all the same thing. They're the piece of software that sits on a client's workstation or the client's computer that does the transaction management. The other component is what we call a data processor, and he's the one that handles getting the data. He is also a piece of software, but he's the piece of software that talks directly to the database. So he may be written in a server-side language like a C# or an F# or C++ or something else that is more code-based as opposed to scripting-based. And he is going to talk to the database, have a communication with him, and bring you back data. His purpose is to give you data. He doesn't handle the transactions, he just gives you data. So he wants those atomic fragments of your query, and he wants to just give you back data. He can exist on the same computer as your TP. So you can have the TP and the DP on the same computer. That's fine. You can have both transaction and data processors on the same machine. Sometimes you don't. Sometimes you can. You can also have a dedicated machine as your data processor. If you need a data processor computer that the only thing it does is handle processing of data, you don't want him dealing with transactions. You don't want him dealing with someone opening up Facebook. His entire purpose is just to handle that transaction or the data processing. So you can have a single computer having both the transaction processor and the data processor. Protocols in general refer to just simply a set of rules that control the communication between the transaction processor and the data processor. So it's one of those words I want to make sure that you understood in this slide was the protocol that explains it. It handles how to synchronize the data and how to route the data, how to get the data from point A to point B, and how to make sure that the data that you have is synchronized with the other data processors throughout so that they all can access the database, they can all get the information that they need. All right, when we talk about distribution of our database, there are different ways to distribute your database. The first is probably pretty common for most small to medium businesses. It is a single site processing, single site data. So we call it an SPSD, single data, single processing. To the processing first. All of the processing and all of the data is all stored in a single computer. So the processor and the data all exist on this front end processor, and he talks to the database, he handles the transactions, he's fine, he gives information back to dumb terminals. Dumb terminals not meaning that they're not smart, dumb terminals meaning that they don't actually do anything, they just send requests and get requests back. So they're kind of, they're not doing any processing at all, they're just sending information to that SPSD, that one processor that handles all of it. So this is your single processor, single data. So your TP and your DP are both the same computer. The second is what we call a multiple site processing and a single site data. So again, our data, our file server, is going to sit on a single location, and he's going to hang out there and do his own thing. He doesn't have to be distributed yet. We haven't moved him around, but we're just talking about a single site data. And then there are multiple sites that process. This is how most client server architecture works. When we do websites, those are usually client-server architectures where the client is your personal computer, it does the transactions, it handles that transaction processing, then sends the information over to the data processor who handles it over there, sends it back, and then they all work fine. So you have multiple transaction processors and multiple computers, multiple sites. They all go through the same network, get the data from the file server and back. Now, when we get into a distributed database system, not distributed processing, distributed database, we can have multiple transaction processors, we can have a dedicated data processor, but we can also have data processors exist on some of our transaction processor computers as well. This is called fully distributed, meaning that the distributed or the data processor that exists on the secondary and tertiary transaction processor computers is distributed. There is data there, and they can access that data without having to go back to the dedicated data processor. Okay, so we store some data on the computers that exist in that situation where both the transaction processing and the data processing exist on the same computer, but you also have a link in the network to dedicated data processors, and then of course regular kind of dumb terminals where they're just transaction processors. Not dumb terminals, that's a bad way of saying it, because they do the transaction processing in there. They're not dumb. When we do this fully distributed system, the processing occurs in multiple locations. The data is stored in multiple locations. Now, having it in multiple locations begs one more level of how are each of those individual instances of our data processing handled. And we have the option between having them all be the same DBMS and having them be different DBMSs. Now, there are some fully distributed heterogeneous DBMSs that handle every type of database. So they have SQL Server, they have an Oracle, they have a DB2, they have a lot of different DBMS systems. They just have implemented the same data model in all of them because for whatever reason, they wanted to do that. There were benefits at the time to be using Oracle for this situation, using SQL Server for this situation, so they created two. And that's fine. As long as they both implement the same model, it's fine. It doesn't happen frequently, but it does happen, especially in situations where people are concerned about being able to run with different database systems. People are concerned about legacy, things like that. Then having them available both in an Oracle and a SQL Server database can allow them to do testing and check things to see which one's the best. Okay, so these are your different levels of distribution. Again, we can do distributed processing if we wanted to have the processing be in multiple locations but the database in one, or you can have a fully distributed system where all of it can be at multiple locations. So when we think about our distributed database system, there's a lot of things that we need to have transparency about. So I'm going to give you the 5 examples now, and then I'm going to do a slide for each of them to explain them better. The first is what we call distribution transparency, which is where, from a user's point of view, you don't care that it's not a single database, a single logical database. You can't tell that it's in multiple locations. So that's the distribution transparency. It's supposed to be where it's transparent, the fact that it's distributed, it works fine, and it doesn't make a difference to you either way that it's in 2 locations or 1, because it all works fine. You can have transaction transparency, which is simply that transactions can pull data from multiple sites without you caring. So I could say if employee data was in California and customer employee information was in New York and I'm in Montana, I can grab data from both of them and I don't notice the fact that they're pulling from 2 different locations. So my transactions are handled just fine without that being a problem. Failure goes into the idea of if one of the sites fails, the others pick up the slack automatically and we don't notice. So the system should continue to work perfectly even if a single site fails. We performance transparency, which is that it should perform at least as well as a centralized database. If it performs slower than the centralized database, why on earth did you change? So you should have kept your centralized database if that was faster. So your performance transparency means that it should be faster and perform at least as well as it did before you distributed it. And then heterogeneity transparency simply means if we have multiple DBMSs, remember I said we could have Oracle and we could have SQL Server, we don't care. They're under the same schema and they work beautifully together and it's fine. So being able to have that integration between the multiple DBMSs means that the homogeneous or the heterogeneous of the database is transparent. We can't tell. It doesn't matter. So transparency is all about the user not knowing the difference between a distributed system and a centralized system, other than that it should go faster. But other than that, and it shouldn't fail as often. Other than that, shouldn't be much of a difference. So with our distributed transparency. So distributed transparency means the fact that it is transparent should not be available or aware to the user. And there are 3 different levels of this. And this is where it comes into, if we are completely transparent, fragmentation transparency, we are at the highest level of transparency and the end user and the programmer don't even need to know that the database is partitioned. It doesn't matter to them. It doesn't change your queries. It doesn't change anything about how you're accessing the data. So that is a fragmentation transparency, meaning that everything, whether there's fragments, is completely transparent. I can't tell that there's fragments. Sometimes we can't do that, so we have to go down a level. The medium transparency level is called location transparency, where we must define which fragment we're going to, but we don't really need to know where that is. So we can say the fragment that holds customer data. And I can just say customer data fragment, and they're like, okay, cool, I know where that is. It's okay, you're good. And I can say, okay, good, because I'm glad I didn't, because I don't even know where it is. So that's location. We don't care where the actual location of the fragment is. We simply need to know what fragment we want. And then we go down one more level, which is our lowest level of transparency, where we must specify both the fragment and the location. We have to know them both. So I have to know it is this fragment I want, and I need it out of this location. So this is local transparency, being able to keep track of the location and the fragment, as opposed to just knowing the fragment name. There are a couple things that we use to do this. Is we use our distributed data dictionary, or our distributed data catalog, which is a system catalog that we use to keep track of those fragment names and the locations they exist in. Yes, it will exist on your computer in your server, and it'll be part of the system directory of keeping track of that catalog in there. We also have a distributed global schema, which is going to keep track of the schema information and make sure that that all stays straight as well. So this will be used to translate your requests if you have multiple requests for remote locations, to tell them where to go. If you do the fragmentation transparency at the highest level where you don't care, this data dictionary and schema are going to help the query managers figure out where that's going to go. So when SQL Server gets hold of it, they're like, okay, well, I know that this table is here, so I'm going to go get that. And this table is here, so I'm going to go get that. Okay. Our transaction transparency is going to cover your ability to handle the transactions from multiple fragments, multiple locations. So we have 4 different ways of describing a transaction transparency. How transparent is it? And these are going to break down into requests and transactions being either remote or distributed. So a remote request is simply a single request to a single remote data processor. Okay, so it's just one SQL statement that is going to a specific data processor. It's all it's handling. It's very simple. A remote transaction would be a transaction going to a single remote data processor. So a remote transaction, remote request, those are things that are going to a specific remote data processor. Distributed versions of both requests and transactions are either a single statement or a transaction going to multiple locations, multiple data processors. So we can have the option of sending a request that involves 2 different data processors in the same request. So if I have a simple SQL statement, but it needs 2 tables, and both of those tables are in 2 different locations, I would need to do a distributed request. If I had a transaction that had requests that went to 2 different locations, that would be a distributed transaction. So the difference between transaction and request, whether it's a single statement or whether it's transaction. And then distributed versus remote is whether or not it goes to one single remote data processor or to multiple data processors. When we do this, we have to keep track of our concurrency control, making sure that all parts of the transaction are complete before we commit anything. So if I have a distributed transaction, let's just go with the most complicated one to start with. If I have a distributed transaction that has multiple statements, all of which are going to multiple locations. So say I have 3 different data processors that I have to access. So I do some stuff in data processor 1, then I do some more stuff in data processor 2, and then I go and do some stuff in data processor 3. Oh wait, something failed. Remember, it's a transaction. I have to make sure that I roll everything back. Well, did I already commit the 2 that were in transaction 1 and 2, or the first data processors 1 and 2? This is where it starts to be a problem. So what we do for this is we handle the 2-phase commit protocol, or the 2PC. 2PC requires that all of the processing has to be written to the logs before the updates are actually done. So we're going to write them to the logs saying, I'm going to update this table, I'm going to update this table, I'm going to delete this table, and they're all getting written to logs before anything ever actually gets processed. Then we follow the data processors to allow them to roll back and forward transactions, to allow them to roll back a transaction and then only roll it forward when we're good. Then we use the concept of a coordinator and a subordinate. So one transaction processor gets to be the coordinator. Everybody else gets to be a subordinate. And that guy is the guy who stands there and he goes, okay, these are all the transactions I need to do. Okay, first guy, I'm going to go and you're going to go run your 2. Did you work? Are you good? Did you do you're ready to commit? Are you good? And he says, yes, I'm ready to commit. And you're like, cool. Okay, hang on. Then he goes over to a second guy and he goes, okay, here's your transactions. You want to go run your stuff. Are you ready to commit? And he's like, hang on. Okay, no, I'm good. Let's ready to commit. I'm good too. Then you go to the third guy and the third guy says, not even close. This isn't going to work. This transaction failed. He's like, okay, cool. Then I want everybody to roll back. So all 3 of them, you tell them all, hey, I want you to go roll back. It's like, okay, cool. If you get to the third one and he says he's ready to commit, you're like, okay, all 3 of you, I want you to go commit and then come back and tell me if you committed or not. And again, if one of you comes back and says, I tried to commit and it wouldn't let me, now I can roll back. So he handles all of that. He's the coordinator. And that's literally the entire process's job. He just sits there and he's like, okay, I'm running some queries, making sure you're good. So you're good. Okay, you're not good. How do I fix you? So with this 2-phase commit protocol of being able to say, are we prepared? It's our preparation phase and our final commit phase. And then we ask the different data processors, okay, are you good? Are you in preparation? Or are you in commit phase? Which phase are you in? You're good. And we handle it from there. Okay, so this is how we handle our transaction transparency when we have a distributed system to make sure that we handle the different transactions at different locations. All right, so we have performance and failure transparency as well. And this is going to handle how the system handles just the performance issues and what does it do if something breaks. So data distribution makes queries a little bit more complicated because sometimes we need to know where that data is located. So it's going to increase the complexity of our query and therefore decrease our performance because we have to do more complicated queries. Because we have to do more complicated queries, our performance may suffer a little bit. So we have to be prepared for that. Hopefully the fact that it's distributed is helping us because we distribute it in such a way that we're hoping it's not going to cause problems. Data replication is kind of an issue. You need to ensure that all of the different versions of any version of a table is consistent across the data. So if I have a different copy, I can do replication. If I have multiple copies of the same database, so I'm going to take the entire database and replicate it, and we'll talk about replication in a second. But if I have multiple copies of the same database, I need to make sure that all of them are consistent. I need to make sure that every transaction that is ever run is run on every one of the replicated databases because they all need to stay consistent. If my data is fragmented in such a way that I don't have to store this transaction on this database because this database doesn't deal with that data, then we're fine, as long as we understand how the data replication works. So the important thing with data replication is to make sure that all of the different copies of the database always stay consistent. Consistency, kind of one of those big things in databases. And then, of course, there's the availability. This is what happens when something fails. So we have network latency, which is where you end up with a delay in your query simply because the network goes slower than you expected it to. There was a lot of people on the internet that day and the network just went slower. And we didn't expect it to be that slow, so it takes a little bit longer. So there's a little bit of a delay in the response times. There's also what we call network partitioning, which is where data is literally unavailable because the network failed. So if the network goes down for whatever reason, because sunspots, I don't know, whatever reason the network goes down, we have to make sure that we can handle that. And how do we handle the availability of the network failing? So because things cannot be guaranteed, we can't guarantee that the world will always be perfect. We have to take those cases and mitigate the risk. How can we handle this if the network goes down? Well, we have a duplicate copy of the database over in this location, and that one should be good. Or we have duplicate tables in this other location. How are we going to mitigate that and make sure you're safe if networks go down? Okay, so like this book tends to do, we did a whole lot of theory in the first part of this. Now we can actually start talking about how to actually break up your database. So we have a database. We have this big, huge centralized database, and we need to break it up because we need to distribute it. So you have options here. And this is where you start thinking about what does your data look like and what can you do to help the data be the most efficient that it can be. The first is how do we choose to fragment our data? Remember, a fragment can be taking pieces of data and putting them in different locations. I can choose to horizontally break up my database. Horizontal fragmentation, horizontal, horizontal, going this direction, different rows. So horizontal is different rows. So I can say I want all of the customers who are in the East Coast to be at the East Coast location, and I want all the customers from the West Coast to be in the West Coast location. Because the odds of needing a customer from the East Coast while you're at the West Coast location is pretty slim, and vice versa. So we can break it that way. We can say based on this concept. So we can say we want to round robin it, we want to pick and choose, we want to use range partitions to decide which ones are getting broken up and how they're getting broken up and how they're being sent. We can also have vertical fragmentation, columns, taking certain columns and putting them in one location and putting other columns in another location. Same number of rows have to exist in both subsets. So essentially you're taking your database table and you're cutting it in half or in sections, and you're taking some of the columns and putting them in one location and some and putting them in another. This would work if you have one table where some of the columns are needed by payroll, but they're not needed by sales. Sales doesn't care. So we can take those columns and put those columns in the database that's closer to the payroll location of where those employees work. And then the sales guys, they don't need those columns, so we can put those columns, we can do the other columns over on the other one. So we can choose to vertically fragment our data. You can also choose to have a mixed fragmentation where you do some data horizontal and some data vertical, depending. I want to still have, my employees cut this way, but I want to have only employees that are on the East Coast over here. So I'm doing a little mix of both horizontal and vertical based on where I want to put things. So that's how you would break your data. And you would do this for each of the individual tables that you're working at. Which tables, and this is where we go back to those modules we talked about, which tables need to be in which location. You may find your entire database needs to be there. You can't break it, and that's okay. That's an option. You can do that with a DBMS, with a distributed database. So when we think about our replication, so data replication is storing multiple copies at multiple sites. How do we handle that? So when we do data replication, what we can do is either one of three different ways, or one of two different ways. We can do a push replication or a pull replication. Now, a push replication means after the update, so we've run an update query. We're going to assume all of queries that modify data as update, so I don't have to keep saying delete, update, insert. I'm just going to say update. So after an update, the data processor sends those changes automatically to the other data processors. So he does his update, he commits his changes. As soon as he's committed, he immediately sends those changes off to the other data processors so they can repeat it as well, so it stays up to date. There is also the concept of a pull replication. Now, if you think about it, a push replication means that the data processor has to do his processing, then he has to create a request, and he has to send it out to all of the different sites, which takes time, takes processing time. A pull replication, the data processor does his update, and then he just sends a quick message over to the other database processors and says, hey, I got some new data. Just saying, just whenever you're ready, I'm good. I got some new data. You do all the work. You come ask me for it, and I'll handle it, but I don't want to spend the energy telling you all of that and sending you the request right now because I got other stuff to do. So I'm going to send you a little request that says, hey, I got some new data. Come ask me whenever you're ready. And then the other data processors will go, oh, well, he has some new data. We got to go get it. So they'll use up their processing power to go get the request and to process it at that point. So it's just the difference of where you want that extra processing to occur. Do you want it to occur on the data processor that is doing the update, or do you want it to do it on the ones that need to be updated? So push versus pull, whether the guy pushes it out to them or whether they pull it from him. When we do our data replication, we have options. We can do a fully replicated, so the whole database is replicated. Everything is copied, every table, every cell, every record, everything is copied, fully replicated. We can do a partially replicated, where we have some fragments, but not all. So we might both have the employees table, but I only have some of the customers and you only have the other half of the customers. So that would be some fragments. We fragmented the customers table, but we didn't fragment the employees table. We fully replicated that one. So you can have a partially replicated, where some is replicated and some isn't. And then we can have an unreplicated database where none of the data is ever replicated. My customers are over here, and I have a table for customers here and a table for customers there, and those two shall never meet. They don't go together. When we have to request customers, we never expect those two to be connected. And there's no duplicate data, which means you never have to have your data processor go ask for data or get it from anybody else, because there's no duplication of data anywhere. So it means that you don't have to worry as much about data replication, but that may not be the most efficient depending on what your database style looks like. When we talk about allocation, where the data is allocated, again, we can have centralized in the entire database in a single site. We can have partitioned, which is 2 or more fragments at 2 or more sites. So at least something is fragmented and there's more than one site. And then we can have a completely replicated, where every database, the entire database as a whole, is stored in more than one location. So centralized versus replicated. Replicated has multiple copies of the same database. Centralized has a single copy at a single location. And partitioned is where we end up with those fragments. That's the distributed part. All right, there is a basic theorem when it comes to distributed databases, and we call it the CAP theorem, because these are the things that are the most important when you are thinking about using a distributed database. Remember, it's not the perfect answer to everything. You really only want to use it in certain situations, and those are when you can be guaranteed of consistency. All of the nodes should see the same data at the same time. There should be no problems with consistency across your data. Availability. Can your data be available all the time? If we want to put a fragment in a location that doesn't have good network access, you're not going to have availability. So you need to be careful about where you're putting your servers, where you're putting your fragments, so that you can guarantee availability at all times. No request should ever be lost. And then again, the partition tolerance. If something fails, the other ones should keep working. This is fault tolerance. Is it going to still keep working? The whole point of distributing, a lot of the points, but one of the points of distributing is to be able to have that fault tolerance where something can break and you're okay. How many times have we seen it where in the internet something goes down and like half of the world goes, oh my gosh, what are we going to do about that? You know, we lose our cell service in Great Falls for a day and the world falls apart because there is no fault tolerance. It can't handle something failing. How do we break that? We do distributed systems so that we have multiple options. It may cost more. It may be a little bit more difficult or more complex, but it does give us back that consistency of being able to be fault tolerant. So there is an option when it comes to this CAP theorem that we talk about, which is the base theorem, which is simply saying it's basically available and it's kind of in a soft state sometimes, but it will eventually get consistent. So eventually it'll be there. It may not be there right now. It might take it 10 seconds. It might take it a minute, but it'll eventually be consistent. And sometimes we have to accept that because you can't guarantee everything perfectly all the time because the world just doesn't work that way. So when we talk about base consistency or base theorem, when it comes to distributed systems, it's basically available. It's available most of the time, like 99.9%, but it's basically available. And it's eventually consistent. Okay, so this is your base system with a soft state, where it's kind of, a little iffy for a period of time. This soft state where it's not consistent yet, but it's thinking about it. It's getting there. It's not available yet, but it's kind of getting there. So that's our soft state. It's not hard yet. It's not solid. It's soft. So basic availability, soft state, eventually consistent. In databases, we love to be able to give you some list of rules, things that you have to follow. This one's in the book. This is your 12 commandments for distributed databases, similar to your 12 commandments for databases, which runs through some pretty similar concepts. Local site independence, central site independence, failure independence, location transparencies, fragmentation transparencies, replication transparency, distributed queries, so on and so forth. These are just the basic things. If you're going to build a distributed database system, do it right and make sure that all of these things handle the way that they're supposed to be. So you can get all of those down. So in summary, in chapter 12 in distributed data, chapter 12, yes, check. So in summary for chapter 12, distributed databases, they're logically related data that's in two physically independent sites. We're going to take our data and we're going to split it. We're going to put it in two places. Breaks the database into two, processing turns it into two network nodes. So the nodes, network nodes, are the things doing the transaction processing, and the database is the thing that exists in the data server. We have our transaction processor versus our data processor. So this is where our distributed processing goes into that transaction processor being in multiple locations. We have our single transaction processor with a single database. We have our multiple transaction processor with a single database, and our multi-transaction processor with our multiple database processors, and that is our fully distributed system. We can have homogeneous versus heterogeneous, where we are all using the same DBMS, or we're using multiple DBMSs. Our transparencies can be in distribution, transaction, performance, failure, or heterogeneity. This is how much is the user aware of? How much do they have to be aware of? We have our transaction requests, which are either our undistributed or distributed requests. Concurrency control, making sure that your database stays current. How do we handle that? Consider your fragmentation and replication types. How are we fragmenting? Horizontal versus vertical or mixed? And then are we doing a partial, a fully, or not replicating? So not unreplicated. And then, of course, we have that theorem of consistency, availability, and partition tolerance, fault tolerance. We really need to make sure that those partitions, if they fail, the system doesn't fail with it. All right, so for your homework, I'm going to have you do almost all of the review questions. I think number 20 was boring, and I didn't like it, so I just kicked it out. But 1 through 19 of review questions. And then, again, for your review questions, please just, tell me what you think. I'm not really grading those harshly on whether or not you repeated word for word from the answer key or word for word from the book. I just want to know if you kind of got an idea. And sometimes the answers can get a little bit long, and I know, and I'd still like to see that you have the information. The problems. So there's only 3 problems in this one. Yeah, sure. So 3 problems. 1 has an A through K, and the answers for A through K are going to be remote request, remote transaction, distributed request. So remember that chapter 12.9 section on that, which is pages 568 through 571, that describe those different transaction types. What they're doing for 1A through K is they're giving you a query and they're asking you, does this look like a remote request? Does it look like a remote transaction? Does it look like a distributed transaction or a distributed request? So those are your 4 answers for 1 through K. You just have to pick out which one's which. Number 2 is asking you, how would you partition the database, horizontal, vertical, or mixed? And then 3, A through F, is going to use the information from number 2 to answer some more questions about why you did things or how you would do things. So hopefully it's not a whole lot of homework for chapter 12, and hopefully you learned a lot about how distributed systems work. Again, if you find yourself in a situation where a system either needs to be distributed or they need a DBA that is going to deal with distributed, being able to know what that means, and even knowing some of this information, is going to put you heads and tails above everybody else, because a lot of people don't know this about distributed networks. But with so much data going on and everything being so global, it's a really good piece of information to know. So have a fabulous week, and I will talk to you soon.